2011 Grade 9 Friar Math Contest. An arithmetic sequence is a sequence in which each term after the first is obtained from the previous term by adding a constant d, called the common difference. For example, 2, 5, 8, 11, 14 are the first 5 terms of an arithmetic sequence with a common difference of d equal to 3. Determine the 6th and 7th terms of the sequence given above. So I will write out the first 7 terms, and let's see what we get. So generally speaking, it's a for the first term, and then a plus d, and then a plus 2d for the third term, a plus 3d for the fourth. You guys get the point. So we are given, I believe, everything that we need to figure out the 6th and 7th terms. So the 6th term, a, well, a is the first term, so that's 2, plus 5 times d, well, d, they told me, is 3. So that would mean this is 17. And then very similarly, that's going to be 2 plus 6 times 3, which is 20. So the 6th term is 17, and the 7th term is 20. B, what is the 31st term? So if if you go all the way up to 31, 31 would be a plus 30d. So just make sure you get that right. And a plus 30d, well, a is 2. 30 times d, d is 3, so that's 92. Yeah, okay. See, if the last term of the sequence were 110, how many terms are in the sequence? Okay, so we are told ... some value n is the last term. Well, n would be a plus n minus 1d, correct? So a plus, I'll do it over here, n minus 1d, they're saying that's the last term, and they told me that the last term is equal to 110. So that's my equation. A I know is 2 from up here, and d is 3, so I guess we just have to solve this basic equation. So this will be 3n minus 3 is equal to 108. 3n is therefore equal to 111, and therefore n would be, what's that, 37? 37, I think. Yeah. Yeah, so there are 37 terms in the sequence. If this sequence is continued, does 1, 3, 2, 1 appear in the sequence? Why or why not? All right, why or why not? Well, if 1, 3, 2, 1 appeared in the sequence, it would basically be of the form a plus nd, right? All the terms are like that. So there'd be some value of n for which you'd be able to get a 1, 3, 2, 1. And we know that a is 2, and n is, well, n we don't know, but d is 3. So let's see if we can figure this out. So this looks like 3n is equal to 1319, and therefore n would be equal to 659.5. Okay, so since n is not an integer, this is not possible, because n represents the number of terms, right? Well, actually, the number of terms would be n plus 1. I got to make that, very careful distinction. But regardless, if n is this, n plus 1 is not going to be an integer. So n has to be an integer because n represents the number of terms, and therefore because n is not an integer in this specific calculation, 1321 does not appear in the sequence. So you can just write that out in a sentence format. Question number 2. You have this triangle ABC, AB equals AC, and altitude AD bisects the base with BD equal to DC. AB and AC is 25, BC is 14. Determine the length of the altitude. All right, so this looks like a basic Pythagoras to me. AD squared plus DC squared is equal to AC squared in that right triangle. So AD squared would be AC squared, which I believe is 25 squared, minus DC, and DC is half of BC, right? So it'd be 7 squared. So that looks like 625 minus 49, and that is 576. Is that right? Yeah, 576. And then therefore AD, you take the square root, which is 24, I believe. Yeah. Determine the area of triangle ABC. Okay, well, the area is going to be 1/2 base times height, like that. The base is 14. The height we just calculated was 24. And therefore, that's going to be 168. Part B, let's move this up. Triangle ABC from part A is cut in along its altitude, AD, as in figure 1. Each of these two new triangles is then rotated 90 degrees about point D until B meets C directly below D, figure 2. The process creates a new triangle, which is labeled PQR. Determine the length of PR. Okay, so let's see what's happening here. Well, let me just remind myself. AD was 24, so this dotted line is 24, right? That's basically what it is on both sides, obviously. And anything else? DC is going to be 7, and BD is 7. Okay, so I think that's all I need. So basically, that means that this is 24 here also. This is 24. So when it's opened up like that, I believe P to D will also be 24, and D to R will be 24, and D to Q is this guy right here, so that's 7. And then these guys, PQ, are 25. So you just have to sort of visually kind of mix and match. Okay, so now that I have it labeled, and hopefully I have it labeled correctly, let's proceed with the questions. Determine the length of PR. So PR looks to me like it's 48. Okay, that's pretty straightforward. Determine the area of PQR. So to determine the area, so that's going to be 1/2 base times height. The base is 48. The height is 7. And therefore, this is 168. And of course, it'd be 168 because it's, even though the shape has changed, it's still the same triangle. Just you cut it in half and then bent it, but the area would be the same as the one up here. Okay, now we get to the final one. There are two different isosceles triangles whose side lengths are integers and whose areas are 120. One of these two triangles, XYZ, is shown. Determine the lengths of the three sides of the second triangle. All right. So, I guess what they're doing is similar to what they did in the previous question, but a little bit of a twist. So first, let me just draw this altitude here, like that. And now let's figure out what we can do with this. What is the actual story here? So let's label this as much as I can. So this will be 15, that segment, and this will be 15 since I cut it in half. And let's see here. The area is 120, right? So 1/2 base, which is 30, times height, which I'll call H for now, is going to be 120. So that means 15H is 120. So H is going to be equal to 8. So that is actually 8. So that's the dimensions of that guy. And then they're saying that there's going to be another triangle that's also isosceles. And I think the way you make that is the same way that you did upstairs, where you kind of just bend it. So let me, this point right here, I'll just call that Z. If I can squeeze it in, I'll just write it up here. So really what you're doing is you're taking the two triangles like this, where this is, let me see, Y, Z, and X. And then same thing, you're just putting them together like this. That's Y's. Oh, there's two Z's. Oh, geez. I'll just call it Z1, Z2. Z1 and Z2. Well, you guys get the point. And then now, once this is joined, it becomes one full triangle, like that, and then the dimensions should be similar. So let's see, this would be 15 now, and then this is 17, that's 17, and then this is going to be 8 and 8, I believe. Yeah, and it's isosceles because two sides are the same. And then, of course, the area would be 1/2 base times height, which in this case is 16 and 15. And that is going to be 8 times 15, which is 120. Okay, so what do they want? They want the lengths of the three sides. So in this triangle, the lengths of the three sides are 17, 17, and 16, because this is the third side. And I believe that's it. Number 3, begin with any two-digit positive integer and multiply the two digits together. If the resulting product is a two-digit number, then repeat the process. When this process is repeated, all two-digit numbers will eventually become a single-digit number. Once the product results in a single digit, the process stops. For example, start off with 97. 9 times 7, 63. 6 times 3, 18. 1 times 8, 8. The process stops after 3 steps, and so on. Beginning with 68, determine the number of steps. Okay, so we started with 68. The first thing you do is multiply those numbers. 6 times 8. 6 times 8 is 48. Okay, you got to keep going because it's not a single digit yet. 4 times 8. That is 32. Still not at a single digit, so keep going. 3 times 2. And that's 6. So that's when the process stops. How many steps did we have to take here? Well, this was our first step, second step, third step. So 3 steps. And I believe that is pretty much what they're getting at in part A. Part B, determine all two-digit numbers for which the process stops at 8 after 2 steps. Okay, we got a little bit of work to do here. So the process stops at 8 after 2 steps. So we got step number 1 and step number 2. And then we have our initial number. Okay. All right. So this is always going to be an 8. So I got to figure out ways of doing this. The first way, of course, is a 1 times 8. And that would mean that this number was 18, right? So how do I get 18? 2 times 9 is one way. And therefore, this initial number was 29. So here's one example that I just did, just based on no real system, just looking at it and trying to figure out what option I had. But obviously, there's going to be more, so let's see. I think there's going to be more of both ways of doing it. So let me just stick with this 1 times 8 and exhaust this first. So 2 times 9, 3 times 6 is another way of getting 18. So that means this number was 36. Okay, I got it. So I just got to fiddle around with this. Another way of getting 18, 6 times 3, because see, even though that's similar or the same, because the digits are reversed, this becomes a 63. And then another way of getting 18 is 9 times 2, which is the same as this, but the digits are reversed. So that means this is a 92. Okay, so I got these 4. 29, 36, 63, 92. Okay, so now let's move on. What's the next one? Another way of getting 8, because 8 is what we have to get, is 2 times 4. So that would mean this is 24. And then I've got to figure out two numbers that multiply to 24, and I believe 3 times 8. So that would mean this is 38. Similarly, 2 times 4, and that's 24. And then what's another way? 4 times 6. 38 and 46. Okay, and then I think the next ones will be just the reverse of the top two. So 6 times 4, which will give me 64, and then 8 times 3, which is basically the reverse of those guys. That will give me 83. Okay, so that completes this. I got another 4. Another way of getting 8 would be 4 times 2, which is the reverse of that, but that would mean this would be 42. And two numbers would be 6 times 7, so this will be 67. And I think 6 times 7 is the only way to get it. So that would be 76, you just reverse it. And then finally, I think there's only one other option, which is the reverse of that guy, which is going to be 8 times 1, which makes this 81, and the only way to get 81 is 9 times 9, and therefore this would be 99. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, I think that exhausts it. So as you can see, it's just a bunch of trial and error. All right, what's next? C. C is next. Determine all two-digit numbers for which the process stops at 4. Oh boy. So it's pretty much the same kind of story. Does it say how many steps? No, it doesn't say anything about steps. So I got to figure out this for all possible steps. Okay. Oh boy. So let me just start with one step, and then I'll do 2 steps, and then we'll take it from there. So one step would be something that stops immediately after you have the initial number. So I'm thinking like 1 times 4, which would be a 14, or a 2 times 2, which would be a 22, or a 4 times 1, which would be a 41. These would be examples of this system stopping at 4 after one step. So now let's graduate to 2 steps. So now we have our initial number. We have step number 1, and then we have step number 2. And the end result is still 4, but this time it's obtained after 2 steps. So this is going to be 1 times 4. And, yeah. So let's see, that would mean this is 14, and you get 2 times 7 as one example, so that's 27. And I think 7 times 2, that would also work, so this would be 72. And I think that's it. Because if we did other ones, like if I did 2 times 2 over on the second step, this would be 22. But then 22 cannot be obtained by multiplying 2 numbers that are single digits, right? Because 2 times 11, but 11 is not a single digit. And similarly, if I did 4 times 1, 41 cannot be obtained by multiplying 2 numbers because 41 is a prime number, if my memory serves correctly. So I think that's pretty much it for 2 steps. Yeah. Okay, so now let's try 3 steps. Our initial number, step number 1, step number 2, and step number 3. All right. Okay, so 3 steps. The last step, of course, is going to have to be the 4. And, yeah. Okay, so this is 14, and then this will be 2 times 7. So I guess I just have to sort of copy what I just did for those last 2 steps. And then this one will be 27. And then can 27? Yeah, 3 times 9. Okay, I got it. So this will be 39. So it's kind of like this helps me to get to this, and then this helps me to get to this part. So at least that's good. Okay, let's keep going here. 1 times 4 is my last step. This is 14. Any other way of getting 14? Any other way of getting 14? Well, there was... okay. I think I have to do this again, because this can be a 9 times 3. So that's how I can get another one. I have to exhaust them. So I think that exhausts it. Yeah. Okay, I think I figured it out. And then this one, again 14, but then the reverse of this. So 7 times 2, that gives me 72. And that would give me like an 8 times 9 situation, which gives me 89. And then very similarly, 14, but again 7 times 2, but instead of 8 times 9, 9 times 8, and that gives me a 98. So there we go, and I think that covers it. So I got what, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Part D. Determine a 2-digit number for which the process stops after 4 steps. So this is one of those, trial and error type questions. So you start off with the initial number, your first step, second step, third step, fourth step. And the fourth step results basically in a single digit. And that single digit, we don't know. So you got to basically trial and error. The single digits can only be anything from 1 to 9. And you just got to, like, I'll give you an example. Let's say it was 1, right? That would mean the only way to get 1 is 1 times 1. So that would mean this is an 11. But then you get stuck because you can't there's no two numbers that multiply to give 11 because 11 is a prime number. So 1 is no good. Then you try 2. And then you say, well, the only way to get 2 is 1 times 2. That would make this 12. Okay, well, that's good because 3 times 4 works. So that means this is a 34. And 34 is 2 times 17, but then you're stuck because 17 is not a single digit. So I don't think there's any two numbers that are single digits that multiply to give 34. So you see what I mean? You get stuck again. So you just got to keep trial and error. So what works is 8. So it's a big, long song and dance. You just got to, go through this. 1 times 8. This becomes 18. 3 times 6 is one option. This becomes 36. 36, one option is 4 times 9. This becomes 49. And the only option is 7 times 7. And therefore that initial number is 77. So that's what works. And obviously when you see it, it makes perfect sense. But coming up with that will take some trial and error. Ian buys a cup of tea every day at Jim Borton's for $1.72. With money from his coin jar. He starts the year with 365 $2 coins and no other coins in the jar. Ian makes payments and the cashier provides change according to the following rules. And here are the rules. How much money will Ian have in the coin jar after 365 days? Okay, so each day he spends $1.72, which is $627.8. And at the beginning, he had 365 $2 coins, which is $730. So he starts with this, he spends that. So the difference, if you subtract it, 627.8, and that is 1022. So $102.20. So that part's pretty straightforward. Now we get into a little bit more complicated. What is the maximum number of 25-cent coins that Ian could have in the coin jar at any one time? So this part is what you have to kind of do a day-by-day analysis. So here's the day. Day 1, day 2, day 3, day 4, day 5, and so on, right? 6, 7, 8, 9, 10, and you just keep going. And then how much he gives, that needs to be calculated. And then what is his change? And the number of 25-cent coins. Number of 25-cent coins. And the number of 1-cent coins. There's other coins, right? That there's 1 cent, 5 cent, 10 cent, 25, and 2. Okay. And then the total. Cumulative total. So I'll explain everything. Don't worry. Okay, so on day 1, in order to buy this cup of coffee, is that what he's buying? I actually don't even remember. Yeah, no, a cup of tea. Okay, cup of tea. I don't even drink coffee, so maybe that's why I don't remember it. All right, so in order to buy a $1.72 cup of tea, he would have to give one of these $2 coins. So he gives this $2 coin. And then he gets 28 cents change, right? Because it costs $1.72. So now that 28-cent change is given in the form of a quarter. So he gets 1 quarter, 1 25-cent coin, which is called a quarter in Canada. And then he gets 3 pennies. And therefore, the change that he gets back is 28. So total change, I should put change in there. Right? So that's all this is. That's it's not anything more complicated than that. And what we're really doing is just concentrating on what does this column get to? What's the maximum can it get to? So here we go. Next day, same story. He gives $2. He gets 28 cents change in the form of another quarter. So now his quarter total is up to 2 because he gets another quarter. And he gets another 3 pennies. So his penny total is up to 6. And his total change is now 0.28 times 2, which is 0.56. Now, on the third day, he wants to again buy a $1.72 cup of tea. But his change is not enough. So he's got to go back and dip into his jar and get that $2 coin in order to buy this. And therefore, this process just continues. This goes up to 3, this goes up to 9, and now it's 0.28 times 3, which is 0.84. Now, the goal is eventually to use the change to buy the cup of tea, but we can't do that yet. Eventually, we will. So I'll just keep doing this. I don't think I need to talk you through this anymore, since hopefully you understand what the process is. But the goal being this total change to eventually get up to that value, so he can then use the change to buy the cup of tea instead of having to keep giving these $2 coins. 5 now, 15, and now we're up to $1.40. We're close, but not quite yet. Gives another 2. 28, this goes up to 6, this goes up to 18, now we're up to 168. Still not there yet. 0.28, now we're up to 7, this is up to 21. Now we're at $1.96. So this is the point where he says, you know what, I've got enough change to buy a cup of coffee. I don't need to keep giving my $2 coins. And then he uses the change. So now watch, when he uses the change, he gives the exact amount. He gives, he basically gives 7. Can he give the exact amount? Yeah, he probably could. I'm trying to think. If he gives 6 quarters, it'll be $1.50. And if he gives all of the pennies, he would be up to 171. Because if he gives 6 quarters, that's 6 times 25, which is 150. And if he gives all of his pennies, it's 21 times 1, which is 21. And that still would not be enough. That'd be 171. He'd still be shy. So he has to give 7 quarters. So he has to give 7 quarters, which is 175. And then his change would be 3 cents this time. This would drop down to 0 since he's given all his quarters away. And this would go up to 24. And now he has, whatever he has, he's given 172 of this 196, right? So he's got 24 cents remaining. Is that right? Well, yeah, because it's 24 pennies. Okay. And then the process continues again. Now he doesn't have enough change to buy a cup of coffee, so he's got to go back and dip into those $2 coins, and therefore he gets 28 cents change. He gets a quarter, and he gets 3 pennies, so this goes up to 27, and now we're up to 0.24 plus 0.28, which is 0.52, yeah, and so on. So as you can see from this table, the maximum number of quarters he could ever have is this guy, because this table will now kind of progress in a way that you will start to see patterns. And those patterns can therefore be extrapolated to figure out what will happen later. So on the 50th or the 100th or the 200th day and so on. And you can figure out how many coins he would have on any of those days later on, since there will be a very predictable pattern. It's just very time consuming to kind of draw it all out.